good reference sheet for you, this first one, because it's a lot of review type stuff. We won't go through all the graphs, though, but we'll go through a lot of these. So let's start with the first one with the power functions. Power function. So a power function is a monomial function, and a monomial function means what? What's monomial? One, it has one term. And so it looks something like this. Yes, that's a power function. Sorry. Okay, so A could be anything and N could be anything as long as they're not 0. Okay, so as long as they're not 0. 4x to the 5th would be a power function. 7x to the 12th would be a power function, okay? So it's kind of it's not really a parent function because you could have that A in front. You could have something there, but it is a monomial. Do you see the difference? Does that make sense? Yes, no, maybe so. Okay. All right. You have 6 different spaces there for different types of monomial function or power function graphs there. And we're just going to do the parents of them. The first being a constant. What does a constant look like? That's exactly right. Equals some number, we'll call it C. Okay. That can go in the little rectangle box that you have. And when you graph it, what does it look like? It's a straight line. That's exactly right. It just does this. This would be the value C here. Whatever that value is, it's just a horizontal line. What's the next type? Linear. That's exactly right. Y equals, but we're going to use f of x because we're fancy. F of x equals x. Okay, so that's a linear function. And what does that look like? That's just a diagonal line straight through the origin. Slope of 1. There you go. There's a linear function. Oh, look, it says on the sheet, a power function is also a type of monomial function. Look at that. Next type, quadratic. You should know this one in your sleep. It's x squared. That's exactly right. Not a V, but yes. We don't want it to come to a point here. We want it to kind of, if it came to a sharp point, what would I have? An absolute value. Y'all are so smart. Moving right along to a cubic. You remember it now? 1, 1, -1, -1, 0, 0, and it does something like this. The dances with the arms. Quartic, which is to the 4th. And although it doesn't look like it on the graph, as you start stretching and shrinking, the humps can start developing in that. You remember how we talked about the humps in it? Right? But the parent graph itself, just the quartic, you really don't see it so much because 0, 0, 1, 1, -1, 1, it ends up looking something like this. That's just a little bit more flattened there, I'll say, right towards the axis, than is the quadratic. I didn't do a real good job. Something about that. Same thing with the quintic. As I adjust and shrink and stretch and everything, some of my humps can kind of start to come out. But in the parent, they're not quite as apparent. Thank you. Thank you. It could. As you start shrinking and stretching, it could end up looking like that. But the parent, if there's nothing done to it and it's just x to the fourth, this is what it looks like. And then x to the fifth really takes on the shape of the cubic. It'll be, if you think about to the fifth power, it's still 1, 1 and -1, -1. But again, it's stretched out a little more towards the axis than is the cubic. Grows a little quicker than the cubic does, but very, very similar. It could potentially do something. Each degree adds another potential hump there, if that makes sense. All right. If the function, and remember, we are only talking about monomials. We're not talking about polynomials. We're talking about monomials. So just one term. So if the monomial has an even power, can you make a conjecture about what's going to happen as far as symmetry? What's symmetry mean? Okay. Well, you were right. But how do we describe symmetry? Two words we use. Even and odd. That's what I was looking for. Sorry, y'all. I was not pushing you in the right direction on that. But even or odd. So if you have a monomial function with an even degree, what do you think the symmetry looks like? Over the y, which is what? Even. Even degreed monomials give us mono. Are you laughing because I can't spell? Sorry. It's symmetric about y, or it has even symmetry. And now if the function has an odd power, odd symmetry, which means origin symmetry. That's exactly right. Good job. You did eat at that. Yep, which means symmetric. Remember, that's where if you twist it 180 degrees, it looks exactly the same. Symmetric about the y-axis, or even symmetry. And then you have a nice little chart down here, and we made that chart in Algebra 2, and here it shows up again, and we can classify in behavior now based on the leading coefficient and the degree. And this works for all polynomials, by the way. But just quickly as we go through, we had an unlimit notation in here, right? Y'all haven't done that yet? Okay. We'll just do our regular old then. We're not going to get into that today. So let's look at the first square. The first square says that the degree is even and the leading coefficient is positive. In the top left square there. And it gives you an example of an even positive. And it does this. What does the end behavior on this one look like? That's exactly right. I'm not going to spend a long time on this because we've done this a gajillion and a half times. Yes. 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 So then if I go over, everything's exactly the same. I'm in an even and negative situation. The only difference is everybody's going down instead of up. It is so hot in here. If it feels good to you, Joyce, then it is very hot. Same. That's what our house is. Russell. Exactly. What, Justin? Their house stays at like 75. I say like 72. 74? Their house stays at 75. I say like 72. Yeah, 72. I'd burn slap up. 60, we said 65. All right, I'm gonna just go ahead and fill this out for y'all. Y'all are so easily distracted. Oh my God. Again, this is review. I don't feel like we need to spend a whole long time on it. Really, the terminology is um, the only thing new here. If you flip it on the back, they're all monomial functions with the exact same kind of analysis that you're used to. So I'm going to scoot on past that, and I'll do an example altogether in just a minute. But let's move on, because this is really what is the new stuff here, and that is our reciprocal functions. Are y'all all with me? Second page, front of, huh? Yeah, power functions with negative exponents. Okay. Sorry. Just tell me when you're ready. Remember we said power functions were this form, right? And we said the only stipulation was A and N couldn't be what? 0. So they could be negative, which puts us in a situation like, what if we have that? Is that a monomial power function? Yes, it's one term, right? And the exponent's not 0. So it's still a power function. And so I can still do all the same stuff, but I'm going to need to look at this a little carefully. Negative exponent means what? You flip it. What is that parent function called? Reciprocal. Okay, so what's the hard part? Well, there is. Here's the thing. Yes, it does. Here's the thing. All the things we just talked about still apply, even in odd numbers. Even in odd numbers can still be negative, right? Yeah. Okay. So what if I have something like this first one? Because a normal reciprocal function, right, does this, and it's odd. Okay, so this is 4 over x squared, which means what? Here's what happens. Anytime you have an even, this is why, anytime you have an even exponent, You only get what out, despite what you put in? Positive. You only get positive values, right? So everything that did spit out negative, I can still plug in a negative, but it's going to spit out, which is my y value. My y value is my spit out value, right? It's going to spit out positive y values. So it's going to take everything that was negative and it's going to flip it up here. So that this is going to look this way instead. Okay? Now it, if the exponent is negative and even, this is what it's going to do. So they will. But remember, that's what we said. If it's an even degreed monomial power function, it's going to be symmetric about the y-axis. When it was like this, it wasn't symmetric about the y-axis. It was symmetric about the origin. But this is why it works, okay? So remember, because anytime I raise something to an even power, it's going to give me a positive value. Yes, it would look like the original, okay? So reciprocals, and this is not, I don't know why it's not anywhere on your sheet, but I would write it somewhere. Even are going to look like this. Asymptotes here and here still, they haven't moved. This would be -2, -4, -6, all still the same. But again, just like with those cubics and quartics and quintics and all that, the more you stretch and everything is, the more that humps and different abnormalities start to appear. But in general, this is what we're going to look like. Say it again. Okay, so this is, I'm glad you asked about positive. This would be a positive leading coefficient. Okay, I'm just showing you the parent for the positive. Of course, if I flip that, then it's still, all my transformation rules are still going to apply. So if I had negative 1 over x squared, it's going to reflect it. Because the reflection would still take over, right? That negative in front, even though everything I plug in is turning positive, that negative is overtaking and forcing everything positive in here. So it's going to flip it over. Same over here. This is odd with a with a positive leading coefficient. If I change that to, say, 1 over x cubed, but then had it negative, of course, then it would be reflected and look something like this. Asymptotes are still in place. I haven't moved them. There's no slides on these because this is just a monomial function. Are y'all with me? Yeah. Okay, so let's look at it because, what you mean? Odd positive is in the green or the blue, whatever color. And then negative leading coefficient, odd negative leading coefficient looks like the red. Because if you reflect that up or reflect it over the x, that's what you have. Yep. All right, so let's just do a couple together. Let's look at them. So for the first one, okay, so we know from the beginning that it's a positive leading coefficient, right? And it's even. So reciprocal wise, what's it going to look like? That's right. They're going to both be up top, right? Both be, I have asymptotes, same places, 0 and 0. Y'all okay there? I'm going to need, and we're going to up the ante just a little bit, I'm going to need at least 2 points on every side of an asymptote. So every vertical asymptote, I need to go at least 2 left and 2 right to pick up a pattern. Okay? So this one's only got one asymptote. We're going to hit some that have two asymptotes. And then if we have two asymptotes, we need 2, 4, 6, 8 points to graph. I know, it sucks sometimes. But since this just has one, I need a total of 4 points, 2 on either side. Okay, and I already know what they're going to do. And since these are monomials, easy points are plugging in 1, right? You're right, because that's right. I'm going to go -2 and -1. And the nice thing about these, when it's even, since it's symmetrical, they're going to be this is the same as f of 2 and f of 1. They'll have the same values, right? Because I'm squaring them and making them positive. Nope, you just need to show the work for the 2. Or if you're using the table in your calculator and you're just showing me what those points are, that's okay too. We just need to get a couple good points on there. All right, so when I plug this in, I get 4, 2 to the -2, which is 4 over 4. What's flipped? Yeah, it is. If I plug in 2, if I do 4 over 2 to the second, you get 4 over 4, which is 1. So at -2 and +2, I'm at 1. Either side of the vertical asymptote. Go 2 left and 2 right on the vertical asymptote. Now if I plug in 1, that's 4 over 1, which is just 4. So 1, 2, 3, 4. Now the reason I did this is I know what the shape in general is going to look like, and I know which direction it hugs, but I just want a little bit of Gina Wilson wants you to use 3 on every side of the, but I think 2 is sufficient on either side. That's what I've always told reciprocal when we graph reciprocal functions, 2 on either side, or rational functions. What's the domain on this one? You remember what trouble y'all had with domain and range when we started? Back in Algebra 2, there were many tears and fights over domain and range. How about the range? That is correct. That as I move left to right from the left, oh, I hit a roadblock right here because there's an asymptote. X-intercept. Why? There's an asymptote. You can't cross that asymptote. Nope, none. Now, unfortunately for y'all, we'll get to some that do have x-intercepts, even though they have asymptotes. But right now, nope, doesn't happen. How about y-intercept? None, y, asymptote. And in fact, for all of these, right, because we don't have any shifts anywhere, that should be none for both of those, for all of these monomial functions. X and y intercepts. There are okay. Yes. Good job. Increasing -infinity to 0, because look, this is the part that's going up. Here's my increasing, here's my decreasing. So increasing is -infinity to 0, and decreasing would be from 0 to infinity. That's exactly. As you move left to right, is the graph going up or down? What do we got? Symmetry. Even over the y-axis. That's exactly right. Either one of those will work. Either even or y-axis. Because they're monomials, that right there tells you. If that's an even number, it's even. If that's an odd number, it's odd. Now, because it's monomials. Now, if there was more, if this was plus 3, that wouldn't work. But for the, oh my goodness. How about discontinuities? X equals 0, there's a discontinuity, and it is an infinite discontinuity. Good job. Pretty soon we will call these continuous functions, and I'll change what you know, but not yet. Yeah. Asymptote. You need to say where it is. X equals 0 at x equals infinite at x equals 0.
We'll see if you got it right on the wrong.
I circled it though.
Okay.
Yeah, because I didn't know what number to put.
All right, how about in behavior? Oh, where am I going? Good job. As x approaches infinity, f of x approaches 0. I'm fixing to change this up on y'all too, but for now. Well, you're going to use this to write limit notation to get you ready for calculus. It's actually easier. It's kind of like when we went from inequality notation to interval notation, and y'all at first were like, eh, but then you were like, that's definitely easier. Why? It gets close to the asymptote faster because it's a fifth. All right, if y'all don't need another one, I'm not going to do another one because they all start to be the same. What do you mean? Yeah? Which one? How about 3 since it's odd? If you got it and you don't need it, your homework page is the last one. There are 6 of them to do. All right, first of all, what's it going to look like before I even graph it? Odd, it's going to be opposite corners, right? Quadrant 1 and quadrant 3. Now, if this was negative like this, it would be switched, and I'd be in quadrant 2 and quadrant 4, right? Y'all know your quadrants as I say this? If it looked like this, if there was a negative in front, it would be, yes, this is 1, 2, 3, and 4. It goes around counterclockwise. Okay. If it's positive, which it is, I'm going to be like this. It is. It is positive, so I'm going to be like the black one. Okay. Yes, it is.
Oh, yeah, it is. I'm looking at yours.
All right, 3 over 2, x to the negative 3. Okay, so let's see. Let's get our asymptotes in first. Asymptote. All right, let's pick some points. One, yes. It could. Let's do -1 and 1. And then you said -2 and 2. Yes, because on this one, it's a little bit different. Now, if it were me, I'd have out my calculator, and I'd have this in y equals, and I'd go straight to my table. And in x, I'd type -1, 1, -2, 2, and I'd find the values that correspond. Second graph. Put 3 divided by 2 in parentheses. Depends on your calculator. I'll show you. It will give you decimals. All right, so here's what I'm going to do. I'm just going to graph these. Witchcraft. No, I'm just kidding. If you go second, yeah, okay. -1, 1.5, or -1, -1.5. 1, 1.5. -2, and here's where y'all get all bent out of shape about how you're going to do it. It's just going to be 0.1. I mean, that's pretty darn close to the axis. I'm just going to put it pretty darn close to the axis. Yeah. Some of them are so simple that it's easier to do it by hand than it is to plug them in, but yes. Yeah. 2 on either side of each asymptote. Yep. The further away you get, though, the closer I get, like if I did a half, it's going to be really, really big. If I did 6, it's going to be really, really small because it's getting close to this asymptote. You see what I'm saying? So the further away you get from the asymptote, or the closer, it's easier just to do the first 2, but whatever. You're not being difficult. Oh, do y'all need me to run through the rest of the analysis on this one, or was it the graph? Yeah. Domain. Yeah. Yep. That's correct. How about the range? The range is the same as the domain. Look from the bottom up. From the bottom and work your way up, and then you hit a roadblock here at 0. None of these will have x or y intercepts. Not for the reciprocal functions anyway, because they have asymptotes at 0. How do you know, Aaron? That's exactly right. Left to right, I never go up. In fact, as I move left to right, I'm always going down no matter where I am, right? But when I'm decreasing, I still need to split it up because I can't say that I'm decreasing on 0 when I don't exist at 0. So I still need to say that negative infinity to 0. Yep. Say again. You don't have an x-intercept. It's never going to cross the x-axis because there's an asymptote. They're keeping it from crossing the x-axis. Odd, which is about the origin. That's exactly right. Discontinuities. I'm still at x equals 0, and it's still an infinite discontinuity. That's exactly right. Be the same for all of these. Yes, ma'am. Then maybe do like 1.5 or something. So you can graph it. In behavior, I hope you're starting to notice a pattern with the reciprocals. They're always the same. They're always going to 0 because that's where your asymptote's at. So much of this, a lot of this is for you to start to see the things that pick up and repeat, because as you start seeing that, you're going to start making connections when we start getting to a little bit harder stuff. Yeah. Yep.